In this video, we'll look at some mole mass calculations. Now, to be honest with you, I don't follow these things step by step. I know that the first thing I need in any stoichiometry problem is a balanced equation. So when I read through the statement the first time, that's really all I care about. When phosphorus burns in oxygen, tetraphosphorus oxide is formed. Yikes! Okay, so I have phosphorus, not diatomic, reacting with oxygen, diatomic, to produce tetraphosphorus oxide, O10, P4O10. It's a covalent compound, so the ratio can be crazy large. I don't have to worry about charges, and you just let the prefixes give you that ratio. I do need to balance it. We're going to need 4 phosphorus, and 5 times 2 is 10 oxygen. Excellent. Okay, so now for the stoichiometry, the good stuff. What mass of phosphorus would be needed to produce 3.25 moles of product? So I have a certain amount of product. I want to know what mass of phosphorus. How much phosphorus do I need? This is such good real-world chemistry. You know how much product you need. So now we go backwards. How much reactant should we start with? So when I do my stoichiometry, I'm given one numerical value, 3.25 moles of product, which is P4O10. I know I'm setting up a proportion. The unit that I have goes on bottom, so I want to cancel moles of P4O10 and switch it to the right substance in your equation. So I want to get over to that phosphorus. The ratio in the balanced equation will let me get over to moles of phosphorus. For every 1 mole of product, I need 4 times as much phosphorus. A 4-to-1 ratio. Excellent. Cancel units. And if I were to leave my answer in moles of phosphorus, I would be done. You need 4 times as much phosphorus. Multiply by 4, that's it. But now these are called mole to mass problems because it says what mass of phosphorus is needed. And mass usually means grams. Okay, so if you plug this in your calculator right now, you would be at moles of phosphorus. We don't want moles, so you can just do one more proportion. Or we'll cancel the moles of phosphorus. We want it in grams. This is just like a mole calculation. Whenever I see grams, I go to the periodic table. The molar mass of phosphorus is 30.97 grams, and the periodic table gives me the mass of 1 mole. So this number right here, I got from my periodic table. Periodic table. I just looked up the molar mass, which is the mass of 1 mole. Now I get it. We've been obsessed with this ratio in the balanced equation, saying that the ratio is a ratio of moles. Yes, you're right. It is a 1-to-4 ratio, but we already used that. Yeah, I need 4 times as many moles of phosphorus. We got that. We already multiplied by 4. Now at the end, I just want to turn those moles into grams. Whenever you use the periodic table, it's always the mass opposite 1 mole, the molar mass. So now you just plug it in your calculator. We're going to multiply any numbers on top, divide by anything on the bottom, which I guess on the bottom I just have 1s. My original number has 3 sig figs, so you can just leave 3 in your final answer. So maybe we'll go, 3.25 times 4 times 30.97. How about 403 grams of phosphorus? Done. That's the only thing different. And that's why I kind of mentioned earlier that you got to get these step by step. If you can do mole to mole, now all we do is add one more step. Instead of leaving our final answer in moles, we want to switch it back to grams. But this is just a mole calculation, switching between moles and molar mass grams. I like that. All right, let's try one more. In the same reaction as above, what mass of oxygen would be needed to produce that 3.25 moles of product? Okay, so we're going to switch from product to oxygen. We start it the same way. 3.25 moles of product, O10. We already know about the phosphorus oxide, so we can cancel moles of P4O10 tetraphosphorus decoxide. This time we want to switch it to moles of oxygen. I check the ratio in the balanced equation. 5 to 1. Cancel my units. You're out. And so again, if the question just said how many moles of oxygen would be needed, done. We'd be done. We need 5 times as many moles. I just multiply by 5. But often in the lab, you would really measure your reactants by mass or grams. So we tack on one more. We're going to cancel moles of oxygen. We want it in grams. The periodic table will give me the mass of 1 mole. In the balanced equation, this is listed as O2. The particle is O2. So then you have to find the molar mass of O2. So we do need diatomic oxygen, 32 instead of 16. And the periodic table gives me the mass of 1 mole. Moles of oxygen are gone. So again, all we have to do is multiply across. I like this stuff. So with 3 sig figs, how about 520 grams of O2? Look at that. Do you see the method? The method is what's most important. And it all hinges on getting the units right on your proportions. There are no shortcuts to stoichiometry. Okay, so maybe some of the mole roll stuff is kind of easy. You could do that in your head. But as you start adding mass, you want to make sure that everything is set up correctly. And if your units cancel, cancel. I can get rid of those too. Then you know everything is set up properly. I love this stuff. How many times can I say it? I love stoichiometry. So again, pause the video and try the next set. Try 3 and 4. It's a double replacement reaction, and you will not need to check any kind of solubility chart. I promise that it works. So if you get the equation balanced, use this one as kind of a model. Start with the moles you're given. Use the ratio in your balanced equation to convert to moles of whatever you're looking for. And then at the end, we're going to use our periodic table to convert from moles back into grams. Alright, so let's look at these guys here. 3 and 4. First time I read through this scenario, all I care about is the balanced equation. How many grams of iron 3 chloride would be needed, so that must be a reactant, to produce 1.85 moles of iron 3 hydroxide, that must be a product, in the reaction between, here it is, iron 3 chloride and sodium hydroxide. Did you get the equation right? A double replacement. Be careful with all your formulas and charges. The ratio should be 1:3:1. Now in this first one, you have 1.85 moles of iron 3 hydroxide. And again, you're working backwards to figure out how much reactant do you need. I get that it's a 1-to-1 ratio, so mathematically, this part right here does you nothing. You start with iron hydroxide, you cancel iron hydroxide. Then on top, I put whatever I'm looking for, iron chloride. In the balanced equation, it is a 1-to-1 ratio, but I still like to put it in there. Then I know I have my unit set up correctly. I get it, mathematically, not a big deal. If you knew that, and you just wanted to say, oh, well, if it's a 1-to-1 ratio, then I have 1.85 moles of iron chloride, and the question says how many grams of iron chloride. And you just have a little mole conversion. Switch from 1.85 moles of iron chloride to grams. That 162.2 off the periodic table. Add it up. I don't need to see work for that. Iron plus 3 chlorine. All you got to do is multiply across, and with 3 sig figs, it was almost exactly 300. And the last one then, with the same reaction, how many grams of sodium hydroxide would be needed? So you cancel what you have, moles of that iron hydroxide, switch it to sodium hydroxide. This time it's a 1-to-3 ratio. You need 3 times as many moles of sodium hydroxide, which is great, but in the lab I'd want to measure my quantities in grams. So then in the end we'll cancel moles of sodium hydroxide, goes on the bottom, moles of sodium hydroxide, and on the top I want it back in grams. 40 grams, mass on the periodic table, and all I have to do is multiply across. My units have all canceled except for the one that I want, grams of sodium hydroxide. If you're starting to feel comfortable, this is good for you. You're in a great place. If there's anything here where you're like, where'd you get those numbers? How did you set that up? Stop in and see me ASAP, as soon as possible, so that we can figure out any misconceptions, any questions you might have before we move on to the next section.